Okay, so let's work this problem. So we have a simple supported beam of length L and load W, and I want to be able to find an equation for displacement and slope.
Okay.
So if I were to cut the structure someplace, and I'll indicate that here. So let's say I cut the structure at some distance x from the left-hand side, and we're looking at either the left-hand or the right-hand side of the structure. Which one would you rather work? Yeah, I think the left-hand is going to be a little easier. So with that in mind, I want to find my reaction at the left-hand side. So let me go ahead and put that in. So let's just say that's a reaction. I'll call that point A. And actually this will be the shear at A, and that's the positive shear at A. And there's no moment. So first what I'll do is I'll find this reaction, then I'll make a free body diagram on the left-hand side, find the internal shear force and bending moment, then use the bending moment and direct integration to find the displacement and the slope. So first thing I want to do is get a concentrated equivalent force. So what's the total area under the load curve? Right, it's a triangle, so it's 1/2 base times height, which is WL over 2. And I'm going to sum moments about B here so I can find AY. So what would be the distance from B to that force? 1/3 the distance. The distance is L, so L over 3. So far so good? Mm-hmm. All right, so let's do that. So I'm going to sum moments. I'm going to use right-hand rule as my positive sign convention. I'm going to sum moments at B equal to 0 for equilibrium. The concentrated equivalent force creates positive moment with my sign convention, so that would be WL over 2 is the force, and the moment arm is L over 3. And then I have the reaction shear, which is negative at a distance of L. So it looks like my shear force at A is going to be WL over 6. Does that sound familiar? That's good? All right. So let's go ahead then and draw the free body diagram for that left-hand side. So there's my free body diagram. A length X. I now have my reaction force at A, which is WL over 6. Let's look at the load. We'll come back to that. Let me go ahead and pencil in the directions for my positive shear force and my positive bending moment. For this problem, all we're really interested in is moment, so we won't worry too much about the shear. What is the intensity of the load there? What would W be equal to here?
WX over D.
There's a couple ways you can do it. You can go back and write an equation for this,
Similar triangle.
and you can use similar triangles. So we know W is to L as this is to X, right? So you're going to end up with WX over L. And you can check that. When X is equal to 0, we get 0. When X is equal to L, we get W. So it matches our load curve nicely. Now with that, we can now come up with the concentrated equivalent force. Now that is a triangle, so that's going to be 1/2 the base times the height. So that force will be what? WX squared over 2L?
Yep.
And we know the distance from the cut. What's that distance?
X over 3.
Yeah, 1/3 of the distance. The distance is X. I'm going to kind of be hard to write it in there, but there's X over 3. It's a little small. Apologize about that. So now we'll go ahead and sum moments again. this time about this cut that we made. Make sure it's in equilibrium. So let's start. The moment is, with my sign convention, is positive. The concentrated equivalent force of the triangular distributed load is also positive moment. And that would be Wx squared over 2L is the force, and the moment arm is x over 3. And then get all the way down here on the end, that creates negative moment of WL over 6 is the force, and the moment arm is x. So we'll solve for the moment. So the moment as a function of x will be, let's see, the first term is going to be negative Wx cubed over 6L minus WLx over 6. One thing you can do is...
No, no, it's not.
What happened? Okay, one thing you can notice is the dimensions. Okay, they both have W over 6. Remember, W is force per length, right? And then look at these length units. This is length cubed divided by length, so that's length squared. And then this one is length times length, length squared. So each of the terms have the same units. Yeah?
Shouldn't that be, since the minus WLx over 6 would...
Oh, yeah. You're right. Sorry. Thank you. That would have been important. Now, before we go any farther, I think we should check this equation. So we know, what is the moment at A?
0.
So if I put in x equals 0, what do I get?
0.
0. What is the moment at B?
0.
And that's at x equal L. So I put in x equal L, and what do I get?
0.
0. It works. So this definitely predicts that the moment at x equal 0 is 0, and the moment at x equal L is 0. So those both check. So I'm feeling pretty good about this right now.
Yeah, right now.
Right now? Okay, so let's kind of break this problem in two. So from my perspective, this is a problem that we've already done a few times, and you can see we're going to build on this basic knowledge to extrapolate to something new. And the new thing is the displacement. So by definition, we know that the slope is going to be the integral of m over EI. That's one of the definitions that we derive. So we're going to do that first. We're going to integrate. Yes, Mr. Isabel.
On the homework, you wrote Q and Y. The Q is supposed to be the slope, right?
Well,
Q, that was a mistake. That's probably the symbol Q should have been mapped over to the symbol font, and it would have showed up as theta.
Okay.
I'll have to fix that.
Okay.
Sorry about that. That's one of those things where I probably changed the font and forgot to go back and put the correct symbol font there. Is that on the homework?
Yes.
Okay. Yeah, I'll fix that. Sorry about that. All right, so let's do this. In our problem, E and I is constant. If you also look at our moment expression, what else is constant? Looks like there's a W and a 6 is constant. So I'm going to pull all that out. So I'm going to have W over 6EI on the outside, and I'm going to be left with the integral of what? It looks like negative x cubed over L, right? Plus XL. And that's not. I don't think that's going to be too challenging to integrate. So let me rewrite this again. So this will be W over 6EI. And then when I do the integration, I'm going to get minus x to the 4th over 4L plus LX squared over 2. And then I'm going to generate an integration constant. Do I know anything about the slope in this beam? Well, from our discussion, we don't. We know that at pins, the slope is non-zero. So we just have to let that sit there. So the next example would be, or the next step would be to integrate the slope to get the displacement. So let's do that. So I'm going to integrate this. So I'm going to leave this W over 6EI out again. So I'll have the integral of all this stuff, which is, I'm just going to rewrite it for you. So this is the equation for that was my slope equation, including the constant. So now when I integrate that, what do I get? I get right, so I get minus x to the 5th over 20L plus Lx cubed over 6 plus C1x plus C2. Before I had this constant, I left the C1 all by itself, so I think I'm going to try to squeeze that back in there like that. I think it doesn't really matter. It'll all work out in the end. Okay, so what do I need to do now? Match my condition. So I have a condition at x equals 0. I know the displacement is 0, and at x equal L. The x equals 0 is probably going to be the easiest one to do first. So I know that at x equal 0, my displacement is 0. That's one of my conditions. So what does that imply? We'll go to this equation and put in x equals 0. What do you get? 0, 0, 0. You just get C2. So that means that C2 is 0. That was easy. The next one won't be so easy. What is the displacement at x equal L? Well, it's also 0. So now, when I put x equal L here, things are going to get a little more challenging. Let's see. So I've got W over 6EI, and then I'm going to have, this is L to the 5th, that cancels, so I got minus L to the 4th over 20 plus L to the 4th over 6, right? And then I've got plus C1L. So really all you have to do is, this is equal to 0. So you need to solve for C1. So therefore C1 is going to be what? Divide everything by L and put all this on the other side of the equation. Now before I do that, what is this? What is this fraction? This is negative 1/20th plus a positive 6th. The common denominator looks like 60, right? So this would be negative 3 60s plus 10 60s is 7 60s, right? So that should be 7L to the 4th over 60. And that would be positive right there, right? Now when I go to the other side of the equation, what do I get? It changes sign. Plus I'm going to drop one of the L's, so I should get minus what? Let's see if I can get all this in here. 7WL cubed over 360EI. Did I do that right?
I'm gonna do it wrong.
Yes?
Yes.
So that means that my final equation for displacement, if I'm still factoring out, to match these other terms, if I'm still factoring out W over 6EI, I can pull that W over 6EI out of here. So I'm going to have W over 6EI. So I'm just rewriting what I've already solved. So that's minus x to the 5th over 20L plus x L cubed over 6. And now I'm going to put this in, which is negative it looks like it's going to be 7L cubed x divided by 60. Is that right? It's looking okay. Let's check the units. These are going to have length units of 4. I got fifth 1 L.
Why did minus 7L through X over 3C?
Well, I pulled 6 out, right?
Okay. That's right.
Now, if this works, what should happen? What is the displacement at x equals 0? 0. So put in x equals 0. What do you get?
0.
Excellent. Should this also be 0 at x equal L?
Yes.
So put in x equal L. What do you get? I think you're going to get minus 1/20th plus a 6 minus 7/60th, which is 0. That seems to be the problem. And since I have C1, you can put C1 back up here and you can find the slope. Now, a second, or actually a third phase of this problem would be what? What is the maximum displacement?
That's what you got to do.
The maximum displacement occurs when the slope is 0. So I would solve this equation, set it equal to 0 and solve for x values. And you're probably looking at that going, holy cow, that's a quartic equation. Well, if you make a change of variable, say z equal x squared, you can transform this into a quadratic. You'll probably only have one quadratic solution that's in the range x equals 0 to L. So you will find that value, and then once you find that value of x, you can simply plug it in here and find the maximum displacement. Probably on the exam I wouldn't ask you to do all of that. I may ask you to evaluate the displacement at some point, but I would say, what is the displacement at, say, L over 2 or something like that. So any questions about this? Is this what you guys got on the homework? Yes? Mr. Isbell, how about you?
Yes, sir. Well, this is the one I couldn't get my thing right. I did number 2 and 3, but I was struggling more.
I
understand it better now.
Okay. What about you, Mr. Randolph? What do you have to say?
I did that on the blackboard, but I thought it was wrong, so I didn't, write it on paper.
Oh, that's too bad.
Yeah.
Always put it on paper, right?
Yeah.
Do any other questions?
What's wrong?
All right, I'll close this down.